Hello everyone. In this video lecture, we are going to understand what is sensitivity analysis. So let's begin. So this is also known as post-optimal analysis because it is done once optimality is reached. That is, an optimal solution has already been obtained. So once we have already solved a linear programming problem, then thereafter we wish to introduce certain kind of changes in LPP's parameters. So we already have seen how does a linear programming problem looks like, what are the components of linear programming problem, there is an objective function, there are the constraints. So wherever in any of the parameters, if you want to introduce a change, then we actually wish to determine what is the effect of that newly introduced change on the optimal solution. So the process is called performing sensitivity analysis. That after you have already solved a linear programming problem, then you want to experiment that okay, if I change the cost or if I change the resource vector, then what is going to happen? So that answer will be obtaining through the process sensitivity analysis. So here I am taking an example to make you understand it better. Suppose you have already computed the profit of a company. So suppose you had a maximization problem, so you have already computed the maximum profit. But say the company's owner is not happy with the outcome, so he wishes to increase the profit and therefore he will introduce certain changes in LPP 1. So the original LPP we are calling LPP 1. So after introducing the changes, we get a actually new linear programming problem, which is LPP 2. So ultimately we want to know what is the optimal solution of linear programming problem 2. So we have two options to get that. Option 1, you have to solve LPP 2 from the beginning and you just completely forget about LPP 1. And option 2 is we perform sensitivity analysis and no need to solve LPP 2 completely, because we don't want to waste the time and effort we have already given to solve LPP 1. Therefore, we actually need to utilize the solution already obtained from LPP 1 and somehow get the new solution just from the solution of LPP 1. So this will be called sensitivity analysis. So we'll be going for option 2. Okay. So actually the sensitivity analysis is having two categories. Graphically it is also studied and algebraically it is also studied. But here we are going to focus on the algebraic sensitivity analysis. And since I'm just talking about that we are going to introduce certain changes. So what is going to be the effect of those changes? So either the introduced changes will be affecting the optimality or it will affect the feasibility. So before proceeding, this should be clear that whenever we are attempting a question of sensitivity analysis or post-optimality analysis, we will be always given the optimal table or the optimal solution, because otherwise there is no point in performing sensitivity analysis. We should be given the problem and the optimal table. So here I have taken just an example, a hypothetical example. Suppose this is the optimal table of a linear programming problem. Then we know that some change we introduce, we'll see that later how we are going to introduce the changes. But here I want to tell you what do we mean by changes affecting optimality and changes affecting feasibility. So optimality is actually controlled by here, because these are the values Zj minus Cj, net evaluations, also called reduced cost, because these values decide whether a given solution is optimal or not. So affecting optimality means this part will be affected, and affecting feasibility means the solution column, the rightmost column where we write XB, the solution of our linear programming problem, that part is actually controlling the feasibility. So these are the areas we have to focus on in the table when we do the questions. So here I am taking first changes affecting feasibility. So we have basically different kind of changes which can affect feasibility, but our focus is going to be on these two. So the first change is you change in the right hand side. So we remember how does LPP look like. It's having an objective function, it's having a constraints and the non-negativity restrictions. So since feasibility is something which is controlled by constraints of the LPP, so therefore the constraints have been focused here, and so we want to change the right hand side of the constraint. So it's usually a constant vector, it can have any value but it's always a constant, there are no variables on the right hand side. So we want to look at the effect of introducing changes in this vector B. So that change is definitely going to affect the feasibility of the problem because these are the constraints. Constraints are always controlling the feasibility of the system. And the second kind of change which we'll be studying is addition of a constraint. So in this video lecture, I am only focusing on the first, that is change in the right hand side vector. So let's explore this case. So here again I have an example. So I have taken an example of a certain company. This is the name of the company, Toyco, which assemble three types of toys, trains, trucks and cars, and three operations are used. These are the daily limits and these are the revenues which you are getting per unit of toy, and you are given the assembly time. So that means all the data is given which is sufficient to formulate this problem as a linear programming problem. So reading this statement very easily I'll be able to write the formulation of this. So I got this formulation. So because there are three toys, so three variables I have taken, x1, x2, x3 denote the number of units of trains, trucks and cars, and so this is the formulation. So usually we are always given the formulation, but here I have given you the formulation, not given you the formulation but given you the LPP, and then we can formulate it. But in most of the questions we are always given the linear programming problem. Okay, so that's the formulation part. And just as now I told you that we are always given the optimal table of the linear programming problem. So the optimal table here of the linear programming problem is also given to us. So this information you will find in every question of sensitivity analysis, the LPP and the optimal table. So now let's talk about what kind of changes they want to introduce. So first part is, if the availabilities of operations 1, 2, 3 are changed to 438, 500 and 410. So see what change it's talking about, these numbers. These are operations, because if you read the statement, each constraint is representing one operation. So now they want to change the operation timings or availabilities. Yeah, these are the times as the unit is minutes. So the data is this which they want to change. So determine the effect on the current optimal solution. So let's see how to deal with this kind of situation. So this is our original LPP. This is a change they want to introduce. 430 they want to change to 438, 460 will be changed to 500 and 420 will be changed to 410. Right. So this is my new LPP, which is LPP 2. So let's see how, without even solving this LPP, we will be getting its new solution just by performing sensitivity analysis. So this is my original right hand side vector. This was the original right hand side vector, 430, 460 and 420, and this one is a changed, the new one, 438, 500 and 410. Here in this example they have simultaneously changed all of them, but in some questions they can just introduce change in one of the values and keep the other two same. So any kind of change can be given, but as a vector completely it is something new. So we have the notation, this is B hat. And now we know this is going to affect the feasibility, and the feasibility is related with the solution, and we know the formula, we know the connection between the solution xb with small b. This is the relation xb is b inverse b. So this is a solution which we are already having. So if you look at the optimal table which was given to you, so this was the solution 100, 230 and 220. So this 100, 230 and 20 is the solution. So here we have not done the computation, I have just shown you for the reference purpose that this information is already with us. So with small b you were getting this xb, so what xb you will be getting with b hat. So that new solution I am denoting with xb hat, The formula still remains the same, B inverse times B hat. So how to read B inverse? All of us already know this, that where to read B inverse from. So from the given optimal table, you read the columns of those variables which were in the starting basis. So you will get very easily the value of B inverse, and B hat is this which you have just seen. So multiply this and you will get this new solution. So that means our new solution has been obtained, and since all these values are positive, non-negative, therefore the feasibility is preserved. That's what the meaning of feasibility is. That means the solution should satisfy the non-negativity conditions, because it's already satisfying the constraints, because it has been obtained from the simplex table. So definitely it's already satisfying the constraints. So for feasibility, it should be satisfying the non-negativity condition. So that's the step. So when you compute new solution, if it remains non-negative, so that means feasibility has not been disturbed, feasibility is preserved. Although values are changed, see, the earlier values were 100, 230 and 20, but now the values are 94, 250 and 34. Values are definitely going to change, but signs are still non-negative, so feasibility is preserved. So what we have to do with this xb hat now, we'll be computing z value, we'll be computing the new value of objective function. So you remember this in sensitivity analysis, whichever kind of change you are studying, whichever question you are attempting, never forget to compute z, because whether optimality or feasibility gets disturbed or not, but you are always supposed to find what changes in the z have been introduced, because that's the ultimate aim. You want to know whether your profit has increased or decreased. So mathematically we need to always compute that. So I have read the new optimal solution. So this was 94, 250 and 34. So this is basically 94, this is 250, and the last one is 34. So if you read this from the table, so this is x2. So x2 is 94, x3 is 250, and this is slack variable x6 34. So obviously when you are computing z, so there is no need to write the value of slack variable because its cost coefficient is 0. And x1, where is x1? x1 is not in the basis, so x1 is 0. So this is your new solution. So you can put the values of x1, x2, x3 into the objective function and get your new value of profit. So you're actually getting an increase in profit. Your earlier profit was 1350, but now you're getting 1438. So they can ask you a further question whether the introduced change is beneficial or not. So yes, this is beneficial and profitable. So that finishes part A. On the similar lines, we have part B. I've just changed the magnitudes. So now the changes are 460, 440 and 380. So this is your B hat. So exactly on the similar lines, we'll be computing XB hat by multiplying with B inverse. B inverse remains the same, can be read from the table. So this is, this time we are looking at the solution is 120, 220 minus 100. So that means one of the components, at least one of the values in this XB hat is turning out to be negative. So feasibility has been disturbed. So that's clear, distinguishable from part A. In part A, all were positive, so feasibility was preserved, but here feasibility has been disturbed. So what to do in this case? So in this case, the first thing you have to do is, obviously you need to compute Z. Z is 1340. So exactly in the same way I have computed in the part A, you can compute this is the new value of Z. But this is not my required or desirable solution because it is not satisfying the feasibility criteria. So I have to get back the feasibility, I have to restore the feasibility. And how to do that? So this solution you just directly substitute into the optimal table. So this one is the optimal table which was given to me. So in the solution column, this complete column is going to be entirely changed. Z value will be this, 1350 will be replaced by 1340, and these 100, 230, 220 will be replaced by 120, 220 and minus 100. So let's do that replacement. So you'll see that we have got new optimal table. Rest values are same, but we have this table. So further this point onwards, because this table is already an optimal table, so it's satisfying the optimality criteria, but the feasibility is not there. So therefore we'll be choosing this as a leaving variable. That means we are actually going to apply dual simplex, because you remember when to apply dual simplex, when we have the optimality but we do not have the feasibility. So you can do that as an exercise. You already know how to do the dual simplex method. So in one iteration you will get your new solution. So you apply dual simplex until you get back the feasibility restored. So this is the new optimal solution which you will be getting. You can solve and verify, and this is the new profit which I am getting, 1290, which is actually less than 1350, the original profit. So in part B the answer is that introduced changes are not profitable. So that finishes part B. So let's move to part C, which is different from these two, in which we have to determine the dual prices and the feasibility ranges. So let's first understand what do you mean by dual price and the feasibility range. So we have these definitions. Dual price is the change in value of Z per unit change in resource is dual price of that resource. So howsoever number of constraints we have, exactly that many dual prices will be having. So dual price is actually the worth of the resource. That suppose the right hand side of the constraint is 430. If you change 430 to 431, you increase it 1 unit, then what is the corresponding change in the value of Z, objective function, which you are going to get? That much is the dual price. So that's the basic definition, but actually it's very easy to compute dual prices from the optimal table. And what is feasibility range? Feasibility range is, this can be understood just by looking at the part A and part B, which we have done so far. In part A, the feasibility was not disturbed, but in part B, feasibility was disturbed. So that means there is some definitely interval that if we introduce the changes within that interval, then feasibility will not be disturbed. However, if we move beyond that interval, the feasibility gets disturbed. So that interval is called a feasibility range. That if you vary 430 say to plus 10 units minus 10 units, so from 420 to 440 if you do the variation, so that's okay, that does not disturb the feasibility, but otherwise it will disturb. So that's just an example. You will better understand it when we'll be actually computing dual prices and feasibility range. So let's do that. So dual prices are actually the value of dual variables, which can be read from the optimal table of primal. So this is a result coming from duality theory, that whenever we are given the optimal table of primal problem, means the original problem which we are focusing on, we can very easily find the optimal value of the dual variables. So the formula is CB into B inverse. And since primal had 3 constraints, so there will be 3 variables in the dual. So the notation is y1, y2, y3. These are the 3 dual variables. And this vector will be CB into B inverse. So you know how to read CB. CB is the cost of basic variables. So you look at the cost of x2 in the objective function, x3 in the objective function, and x6 in the objective function. So you substitute it there, and B inverse you already know. So you multiply, you will get this 1 to 0, which is basically written here 1, 2 and 0. So these are the dual prices of 3 constraints or 3 operations, because in this particular example each constraint is representing one operation. So dual price of first operation is $1, because in this example all the money are given in dollars, so I'm using that unit. Dual price of second operation is $2. So this has to be in order. This is of 1, this is of second, this is of third. So we have obtained the dual prices. Now we want to obtain the feasibility ranges. So feasibility range you have to compute one by one. So let's first compute feasibility range of operation 1. So this is the original right hand side vector 430, 460, 420. Now since I want to know the feasibility range of first constraint, first operation, so I'll be only introducing the change in first value. So let this 430 be changed to B1, because I want to know what is the level of changing, how much should it be changed, how much it can be changed. So since that is an unknown, so let's call it B1, and then rest 2 remain same. 460 remains 460, 420 remains 420. So remember, when computing feasibility ranges we can only vary one at a time and keep the other two fixed. And then the same process with this new b hat, I'll be computing new x b hat using the same formula, b inverse into b hat, but this time the solution which I am getting is not a numeric value, it's actually turning out in the variable b1 in terms of b1. And then because we are computing the feasibility range, so we want to know that what is that condition which will keep this newly obtained solution feasible, non-negative. So for feasibility to be preserved, you put this condition x b hat should be non-negative. So that means this as a vector should be non-negative. So that means it's three components, it's all the three components should be non-negative. So see, second component is 230, it's already non-negative. But so from 1 and 3rd you will get two conditions. From 1 you will get b1 should be greater than equals to 230 and then b1 should be less than 440. So this interval is called the feasibility range of operation 1. So that means its original value was 430. So this 430 is definitely in this range. So you can minimum take this value to 230 and maximum you can take this value to 440. So if you vary this within this range, the feasibility remains preserved. Value of the solution changes, but it does not become negative. And similarly, on the similar lines, you can compute feasibility range of operation 2 and operation 3. I have directly written the answers, but they are very easy to compute.